Okay, so planets. What would one say about planets? Well, you know, the planets are the brightest objects in the night sky. And that means that depending, of course, on where they are with respect to when you're looking up, because they're going around the sun just like we are. So sometimes they're on the other side of the sun, and of course, we can't see them. But when they are in the night sky, that means that it doesn't really matter where you are and how bad your light pollution is, you can see them. And some of them, most of them, are actually delightful to see through a telescope or even binoculars. When I talk about planets, I'm actually including the moon. It's not strictly a planet, it is a satellite. It is a moon, it goes around a planet. But we'll talk about the moon because, you know, when you think about it, there really aren't too many planets where we, sitting on the surface of the Earth, can actually look at somebody else's geography in detail. And we can see the geography of the moon in detail. So let's remember what these planets are. They're part of a solar system. That solar system is 4.5 billion years old. The planets probably formed very soon after the proto-sun was there. In other words, something which was glowing in the middle of this rotating disk, which people would have said, well, that looks like a star to me. But it would have been a proto-sun because it was still evolving. And the remarkable thing about the planets in our solar system is that they approximately rotate around the sun on circular orbits. They're not, they're ellipses. And they're approximately in the same plane. They're not, they're actually in slightly different planes. But when you compare this to the new observations on what they call extrasolar planetary systems, in other words, planets around other stars, it turns out that our solar system is actually quite remarkably well behaved. In many other cases, the planets are on highly elliptical orbits. The planets in our solar system are quite evenly spaced, whereas in other solar systems, they tend to be bunched up really close to the star. And in some cases, for example, you have huge giant planets the size of Jupiter, we'll talk about Jupiter in a minute, which are in so close to the star they're going around that they're actually almost as close as Mercury, which I'll talk about in a minute, is to our sun. And then it turns out that between that huge planet and the star it's going around, there are 4 or 5 other planets in that small space as well. So our solar system is nicely spaced out, which is good because it actually helps it remain stable. Now, of these planets, the planets which I would refer to as the rocky planets, that's Mercury, Venus, the Earth-Moon system, and Mars, those are essentially made of rock. And the outer planets, which would include Jupiter, Saturn, and Uranus and Neptune, they are made essentially of gas and ice. And we'll talk about those in a minute, but the thing is, the gas and ice planets tend to be what they call giant planets. They're way bigger than the rocky planets. Mercury, of course, is the smallest one, but it's odd, and we'll talk about that. I will mention the Earth and Moon, because they are, of course, the planet we know best. And so we hold the Earth-Moon system up as a yardstick sometimes and compare everything with us. So let's move ahead here. Here are the planets in the solar system, obviously going around the sun. Let me get my annotate, there we go. This gives you an idea of the relative sizes. So the giant planets clearly are bigger than the rocky planets. Whereas this set over here gives you an idea of their orbits around. They're not spaced to scale. Let's be quite clear on that. So Mercury is the closest rock to the sun. Here we are, we're the 3rd rock from the sun with Venus between us and Mercury. And then there's Mars. So let's actually move on from there. I've got to get rid of that. I think I have to, there we go, I have to do it that way. And what do I have to do here to get this to, there we go. So let's start with Mercury. Mercury is the closest planet to the sun. It looks like the moon, but in fact, it's really quite different. It was quite recently re-examined by NASA. They sent a probe called Messenger to orbit around it. And MESSENGER stands for Mercury Surface Space Environment Geochemistry and Ranging. Geophysicists like to have cute names for their programs. And it seems to me they actually name the program according to the cute name they've come up with rather than the other way around, but let's pass on that. It's a small planet, but it's got some very peculiar characteristics. And in fact, these characteristics are so peculiar that they really call into question our entire understanding of how planets form. We think that planets form by the accretion, the sticking together of small bits and pieces of rock, dust, and gas that were going around the sun as the solar system was forming 4.5 billion years ago. And the idea is that these things all stick together. The act of sticking together, since things are moving very, very fast, they're actually colliding together. That actually releases a lot of heat. Since motion is energy, energy is heat, and you can convert from one to the other. And the idea is that the planets would have heated up, probably melted internally, and the heavy parts like iron and nickel would have sunk down into the cores of the planets, and the lighter stuff, like oxygen, silicon, carbon, and what have you, would have floated out towards the external part. And the thing is that in the case of Mercury, we're facing a most peculiar situation. It turns out that its core, let me just see what my next slide is so I can remember. There we go, that's what I was looking for. It turns out that its core of iron and nickel is way, way, way bigger than we would ever have expected, according to this standard model of planetary formation. So let's just have a quick look at this standard model. Here's the standard model right here. Okay, I've got to get, oh, no, I want to go back one. I annotate. Oh, I can't see annotate. That's unfortunate. Okay, the green sphere with pink stuff in the middle, which says upper mantle, lower mantle, core, with a white background. That's a standard model of what a differentiated planet should look like. Where the pink is the core, that's where the iron and the nickel is, and there's sort of a what would you call it? Nasty green looking thin stuff on the outside. That's the crust, and the green in between the pink and the crust, that's known as the mantle. Well, in the case of Mercury, as you can see in the lower right, it turns out that iron nickel core is enormous. It's forming 80% by volume of the planet. So the big question is, where did the rest of the planet go if Mercury formed as a standard rocky planet? And there are several hypotheses, collisions with other planets, or perhaps the early sun, when the Mercury was close in, maybe the early sun burnt off the outer layers. As I say, there are a number of these hypotheses, but it turns out that if that's the case, then if you've blown off the outer parts of the planet, then there can't be a crust. And the mantle is very, very thin compared with the standard rocky planet, so there won't be much mantle either. Now, you'll notice up in the top right-hand corner, I've got an image there of Mercury. It's what Mercury would look like if you were actually coming in close to it. And you notice there's a lot of blue. So if I go to the next slide here, here's a lot of blue. This is a map of Mercury. It's rather like the atlas maps you see of the Earth, where you take a sphere and you basically undo it, flatten it out, and then you distort the polar regions so that it fits onto a rectangle. But the important thing is you can see a lot of blue. That blue, it turns out, is carbon. It's graphite. It's the same thing as pencil lead, if you're old enough to remember what pencil lead is. Now, I really would like to be able to draw on this if I could. I'm just looking to see if I can find out where. No, I can't find my annotator. Oh, wait. Oh, hang on, draw. There we go, draw a squiggle. Oh, very good. Okay. If you look over here, you can see that there's an impact feature in gray, that's a crater, and then around it is darker blue than the other blue around. What that tells you is that meteor impacts or asteroid impacts into the surface of Mercury have been digging up carbon from just underneath the surface. There's another one right here. A nice blue circle around a gray core. So what this is telling us is that the carbon isn't actually only at the surface, it's actually mixed all the way through, at least the upper 5 to 10 kilometers. Now, how did that carbon get there? Why does Mercury have so much carbon at its surface? We have carbon on the Earth, but most of the carbon we have on the Earth actually is sitting in plants or animals, not just lying around on the surface. If you think, well, we have coal, oil, and what have you. Yeah, but that's animals and plants which actually died, accumulated, then turned it back into carbon. This is inorganic carbon sitting on the surface of the planet, and it's unique to Mercury. Well, it turns out that Mercury has a rather special composition with respect to oxygen. It doesn't actually have that much oxygen around. It's technically referred to as being reduced rather than oxidized. And it turns out that if you actually form Mercury as a reduced planet, chemically reduced planet without much oxygen, then when the planet begins to heat up and it actually all melts in order to differentiate, it turns out that the only thing that's light enough to float to the surface of what's called a global magma ocean is carbon. That means that the carbon represents the primordial crust of the early planet Mercury, which means that all of the hypotheses that suggest that Mercury has a huge, let me see if I can go back one. No, apparently I can't. That Mercury has a huge core because the outer part of the planet was knocked off somehow, cannot be true. The early crust is still there. So we have to come up with a totally new model to explain why Mercury, as a rocky planet, has not formed the same way other rocky planets formed. Well, it turns out that if it formed in a part of the solar system that was highly reduced, in other words, not much oxygen, it would have turned out like this. It would have actually had a lot of iron. But that just raises the question, why was the inner part of the solar system reduced and low in oxygen when the rest of it wasn't? So basically, we still don't know what's going on. So let me see if I can clear my annotations, and I think that might then allow me to control things here. I'll get it in a minute. Clear my, move on. I appear to be stuck, and I'm not sure why. Let me, bear with me since I do have a second or two. Let me get rid of this. Let's see. Yes, it does. Okay. All righty. So let's move on to Venus, which is the next planet out, the second rock from the sun. Venus, you've probably noticed it in the evening sky to the west, southwest. It's that really bright star. Of course, it's not a star. It's a planet. Right now, it would be called the evening star. When it rises in the morning, it's called the morning star. We'll look at that in just a second. It's very, very bright because it's completely surrounded by opaque clouds of carbon dioxide. So the surface, which you can see on the left here, is actually totally invisible to us, at least in white light. And the only way that we can actually see the surface of Venus is by using radar. And we have only sent one radar dedicated satellite to Venus to map the surface, map the bedrock. And that was back in the 1990s, the early 1990s, from 1990 to 1994. And that satellite took 4 years to map the surface of Venus. Now, Venus is commonly called Earth's twin. Yes, but it's very, very different. Let's see what comes up next. There we go. This is a radar map of the whole of Venus, the whole thing. And you'll notice immediately that if it's supposed to be Earth's twin, there are several things that are missing. Number one, I don't see any ocean basins. I don't mean water. I don't see any basins into which water might or might not have flowed. The Earth has basins, ocean basins. Even if you took the water out, they would still be there. And I don't see any continents. The continents, of course, stand high, and the ocean basins stand lower. One of the features of Venus is that there isn't actually very much variation, globally speaking, in height. Other thing that's missing here is, although I do see a few round features, I can see one. Let's take a risk here and see if I can. Whoop! I didn't want to go there. Where would I find? Oh, I'm not going to try and draw on this. Down towards the lower right, you'll see a circle. That circle is about 2,000 kilometers across. And it's known as Artemis, in case you've ever heard of it. But apart from that circle, there aren't too many major impact features that you can see. They're there, but there's probably only about 1,000 compared with the hundreds of thousands that there are on the Moon and Mercury. And this tells us that the surface of Venus is relatively young. By relatively young, I mean scientists are talking about somewhere between 300 million and 800 million years old. And what they're suggesting is that sometime during the window, I'm hearing other microphones. Sometime during that time period, there was a volcanic episode whereby Venus, which had heated up inside because it contains radioactive compounds and radioactive elements, just like the Earth does, uranium, potassium, this kind of thing. Venus's surface was completely resurfaced by volcanic lavas. Think springtime when the municipality starts to fill in potholes and they're resurfacing the road. Well, Venus got resurfaced in somewhat the same way. Let me see what the next slide turns out to be. Oh, I see. I have to, there we go. Now, I'm not going to get into the details of Venus. I'm not going to get into the details of what it looks like because I may be actually specifically talking to you about Venus later on this afternoon or this evening, depending on the cloud cover. But the one thing I will point out about Venus is that it has the largest coherent structure in the entire solar system. There's that circular, oh, let me get that, I'm going to take a risk in that to get that annotate thing back. There's the, no, it didn't want to do that. Let me go back, there we go. Okay, you can see Artemis in the middle there. It's that circular feature. And it has all these other circular features. Most of them are actually lines on the ground, but people are not really exactly sure what they are. There's circular features which are concentric, linear features that are concentric, and there are linear features that are radial. And that entire structure there, at least the white circle there, is something in the order of 13,000 kilometers across. That's pretty big. And it's, as I say, it's the largest coherent structure in the solar system. It's interpreted as some form of updoming. No one's quite sure why it would have happened. Was it a response to a major impact, perhaps on the other side, perhaps on this side? Difficult to say. It is supposedly a relatively recent feature, which means that it can't really be too much of a large impact, because there wouldn't have been time necessarily to move it all over with volcanic lavas. But the thing is here, though, that the size of this structure certainly puts a lot of constraints on what its origin must be. It's probably not some form of localized origin within the planet.
Simon, we have a question.
Okay.
Why is Venus so bright?
Oh, Venus is so bright because that carbon dioxide atmosphere is reflecting most of the sunlight that falls on it. If you look at the Earth, you just look at clothing. If you wear black clothing, it absorbs light, and so black clothing is warmer in the sun, and white clothing reflects light, and so it's cooler. Well, Venus is the same thing. Since you can't see any rocks, the white clouds are reflecting most of the light back. It's referred to technically as the albedo. Whereas other rocky planets, there are dark parts to those rocky planets, and so they're absorbing part of the light. That's why Venus is so bright.
Okay, thank you.
So the Earth-Moon system. The Earth-Moon system is the most intriguing feature in the solar system, not just because we live here. Look at the size of the Earth compared with this gray feature here, which is in fact a picture of the moon at scale. And you can see that the moon is clearly smaller than the Earth, but it's actually huge compared with the Earth, because our moon is approximately the size of the 4 moons of Jupiter that you can see through telescopes going around Jupiter, and you can see them through binoculars as well. So moons like Callisto, Ganymede, Europa are about the size of our moon, except that they're a planet which is 100 or more times the size of our planet. So our moon is actually huge compared with the size of the planet that it's going around. And that's really very lucky for us, because a smaller planet like ours, spinning on its own axis, would actually wobble like a top, like a child's top. It wouldn't fall over, but it would wobble, it'll wobble. Mars, for example, doesn't have a very large moon. And it has an axis of rotation, which is inclined, just like the Earth's axis of rotation is inclined, about 25 degrees to the plane of orbit. And Mars wobbles. It wobbles quite significantly on a time scale of maybe 100,000 years to 1,000,000 years, which means that the climate of Mars cannot be stable, whereas our climate is stabilized at geological time scales, thank you, because of the presence of our huge moon.
Simon, we have a couple more questions about Venus.
Okay.
First one is, why is it the hottest planet?
Oh, it's the hottest planet for 2 reasons. One is it's relatively close to the sun compared with us, but the most important thing is that CO2 atmosphere, carbon dioxide atmosphere. It's 99% carbon dioxide. We all know about the greenhouse effect due to carbon dioxide. Well, if you have a greenhouse effect on a planet with no water, because the principal greenhouse gas on Earth is water, but if you take water out from a planetary system, then carbon dioxide is the greenhouse gas, and Venus has an overabundance of it. And so the heat that comes into the Venusian atmosphere from the sun and is conducted down towards the surface, or actually manages to penetrate through the CO2 cloud cover, cannot actually radiate back out. And so the surface of Venus is approximately 450 degrees centigrade, which is hot enough to melt lead.
Okay, second question is, can you explain the reason for the reverse rotation of Venus?
The reverse rotation is probably because Venus has been knocked over. In other words, when it was upright, it was actually rotating in the same sense as the other planets. And the one hypothesis is that it got knocked right over. One of the problems with that hypothesis is that the rotation axis of Venus is almost at 90 degrees to its plane of orbit, which would be quite a coincidence. Another possibility is that it's to do with the winds. The Venusian winds blow in the direction in which the planet actually rotates. But the problem with using the wind to actually drive the reverse rotation is that as you go down into the cloud cover towards the surface, the winds die down. And in fact, if you could stand on the surface of Venus, you probably wouldn't even feel a breeze. You'd burn, but you probably wouldn't even feel a breeze. So people are still arguing about what exactly the cause of the reverse rotation is.
Okay, I'm going to turn the hosting over to Doug, and Simon, you've got about another 15 minutes to go before JS comes in.
Okay, then where am I here? Okay, so the Earth, of course, itself is unique. It has plate tectonics. And plate tectonics, I won't go into the details of this. This is what allows the plates to move around. the fundamental thing is that in the oceans, there are these ridges, which you can see here in the blue areas. And those ridges are areas where the interior of the Earth is welling up. And then there are subduction zones where the ocean floor dives down under the continents. And this is what actually allows the Earth to gently cool. Here's the spreading ridge in the middle here. And on either side, you can see the subduction zones, above which there are volcanoes. This is a Mickey Mouse diagram, by the way. There's lots wrong with it, but it's useful for illustration. So the Earth is able to cool, luckily, and it's the only example of a planet that we know of that actually has this ability. Let's turn to the Earth's moon. The moon is the product of a magma ocean crystallization. It has two faces. It does not have a dark side. It has a near side, which always looks at us, and it has a far side, which doesn't look at us. And they are quite different. There are, again, all kinds of hypotheses on exactly why they're different. It's thought that there's a difference in the thickness of the crust. On the near side, the crust seems to be thinner. It seems to be thicker on the far side. And again, there are all kinds of hypotheses as to what might cause that. So I'm not going to get into that. But I do want to talk about this imaginative image here of a collision between the Earth and some kind of planetary body. It's actually got a name. It's called Theia. And the idea is that this collision would have occurred. It would have generated a ring of debris derived both from the collider and from the proto-Earth. And that debris would then have collected together and heated up in part by the force of collisions between the fragments, but also partly by the heat of the original collision itself. And the latest thinking on this is that what probably happened is that maybe everything, including the Earth, actually got caught up in this collision and complete destruction of what was there, forming this cloud shaped like a donut. And from this cloud, the Earth would have formed in the middle, and the moon would have formed from the outer part of the donut. And the reason this is important is that one of the problems that planetary scientists have been having is explaining why it is that the Earth and the moon are chemically so very, very similar. No, they're not the same rocks, but they do have the same isotopic composition. And one of the big problems there is trying to get everything to mix up so that stuff from the Earth and stuff from the collider would actually then end up thoroughly mixed so that the Earth and the moon would have the same composition. This is the latest idea suggesting that this is what actually happened. Now, one of the important things here is that this collision was random. And this again brings us back to this rather remarkable Earth-Moon system. Not only do we have this wonderful large moon stabilizing us so that our climate is stable for 4.5 billion years practically, or at least at that scale, but that life can actually then evolve in a stable environment. So let's move on from here. Let's move on to Mars. Mars on the left, that's what Hubble can see. And Mars on the right, that's what you'd see if you were actually orbiting Mars with a probe. Even Hubble really can't see much. It sees light patches and dark patches. Of course, the light patch at the top is a polar ice cap. The red is essentially dust and sand with iron oxide. Essentially, it's moving sand. And the dark stuff, that's black basalt lava. On the right, you can actually see some of the major features of Mars. I'm going to move through that picture to this one, which has it's intentionally got a vertical exaggeration to it. But here you really can see the geography of this other planet. You can't see it this well from Earth. You can only see the geography of the moon this well from Earth. But here you can clearly see there's this east-west gash, rather complicated looking. It's actually the largest valley system in the entire solar system. It's called the Mariner Valley after the probe that actually first managed to clearly photograph it. Its length from one end to the other is the same as the distance from Vancouver to Halifax. To the left, those three bumps in a row there, those are three huge volcanoes, and they're sitting on a massive plateau. It's called the Tharsis Plateau or Tharsis Uplift. And that's the biggest plateau in the solar system. And it's actually higher, way higher than Everest. And then you stick those volcanoes on top. And
Simon, I have a couple of questions.
Okay.
Good that you can hear me. What is the Barry Center? Could you explain?
Can I get through this first and then take the question?
Sure. Yep. Go ahead. Yep.
If you look to the upper left, you'll see another big volcano. That's Mount Olympus, and that alone is the biggest volcano in the entire solar system. And the stuff out on its towards the upper left from it is considered to be material that's slumped off from the volcano, a gigantic landslide. What were the questions?
So the question I've got here from, I've got one from Daniel who's on point. It's, what is the Barry Center? Can you explain that?
What is what?
Barry Center.
A Barry Center?
Yeah.
The Barry Center, if you've got two objects rotating around each other, for example, the Earth and the Moon, then as I recall, the Barry Center, no, I'm going to get confused on this one. I think the Barry Center is a center of gravity, but I'm not sure if it's the center of gravity between two objects or offset from the center of one object.
Okay. Now the other question is a little bit beside the topic, but maybe you could answer this a bit later. Well, apart from the sun, which star's light reaches the Earth? And I think they're asking, you know.
That's a good one. The stars whose light reaches the Earth and that we can see as stars are all stars not only within our galaxy, but within the very local part of our galaxy. I'm actually mentioning this when I talk about galaxies and clusters later this evening. Okay.
Okay. I'll make note of that and remind you later on.
Fine, let's do that. So
okay.
Geography is wonderful stuff. And as I showed you, that was larger than life. Mars has a wonderful geography. It's got in the reds, yellows and greens here, this is highland country. And then in the blues, especially on the north side, that's the lowlands, the northern lowlands. And the reason that the northern lowlands are very important is that no one's quite sure what they are and how they formed. One of the major hypotheses is that in early Mars history, that there might have actually been an ocean, and that we'd be looking at the ocean floor here, which would mean that the boundary between the reds, yellows, and greens and the blues on the northern side, that would be a shoreline. It's up for grabs. It's certainly something which people are paying a lot of attention to, but then, you know, as they say, water is life and life is money. And when it comes to getting money for major research projects which cost billions of dollars, politics does play a role. And talking about looking for water and life, more resonance than going and looking at the geology of rock. So since I don't have too much time, am I right that I've got about another 7 minutes?
Yep.
Okay. This is Mars, by the way, before we leave it. If you were standing there, this is, I think Curiosity took this picture. It does look as though you're standing there. So does this. Mars today, of course, is a cold, dry rock desert. So if there is any water, it either escaped through the atmosphere, or it's actually locked up as permafrost underground. So that's an artist's impression of what maybe the ocean on Mars might have looked like. So let's turn to the gas and ice giants, and let's do this briefly. Since they have many features in common, and you can't see much more than their atmospheres, but this is really the key message that I wanted to bring home with respect to the gas and ice giants. Jupiter is a wonderful sight. You can actually see it from your backyard through a telescope. And you can indeed, even through a relatively small telescope, see some of the bands that you see here, the horizontal bands. On the right-hand side is one of these super most recent is taken by the Juno probe. And you can see that the resolution in the details is just extraordinary. You're looking towards the South Pole, I think, on that one. But the image on the left is more like what you might see bits of if you're looking through a small telescope. A big telescope will show you this, and a camera on any telescope could show you this. the red spot there. Lots of discussion about whether or not it's getting smaller, whether it's fading away or not. And again, there's all kinds of schools of thought on this. But the key message here is what you are looking at here. You are looking at clouds. And if you're looking at clouds, then you're looking at weather. You are looking at the weather of another planet. And I think that's something quite extraordinary. The very circular things and the what have you, they are storms in the atmosphere of Jupiter. Saturn also has its own clouds with its bands. And so again, you're looking at weather, but the weather is a lot less turbulent. The really key question with respect to Saturn, of course, is the rings. Everybody wants to know whether or not those rings are new or whether they're old. And one of the hypotheses is the rings have to be recent because otherwise they wouldn't be so clean and bright. If they were 4.5 billion years old, the idea is that with all the bombardment from the solar wind, they should have darkened. And so a lot of the debate about Saturn turns around the idea of how do you actually keep the rings clean? Did they form recently and that's why they're clean? Or are they dynamic? Are they constantly forming and reforming each other, themselves? I put the other image in on the right-hand side because this one has a key feature, which again, you can see through a telescope. And that is that Saturn actually casts a shadow on its own rings, depending, of course, on its orientations. Moving further out, those Saturn and Jupiter are what are referred to as gas giants. And as you move further out in the solar system, so the average temperature of the solar system decreases further away from the sun, and so you get a lot more water ice in the system. You also get ammonia ice and what have you, methane ice. And this is Uranus. I wanted to show this slide here for two reasons. One, the color. It's got this beautiful blue color, and you can actually see this through a telescope. For some people it's blue, for some people it's green, it depends. But the important thing is that we're seeing these colors here because methane, which is very common in the atmosphere of Uranus, it absorbs the red color of the spectrum. And so what bounces back to us is blue. The average composition of the upper atmospheres of both the gas and the ice giants are essentially hydrogen and helium, plus or minus ammonia and methane. And just as with Jupiter and Saturn, you could see weather going on in the upper atmosphere, so you can see the same thing here. Compare the image on the left with the image on the right. They're taken a couple of years apart, and you can clearly see that on the right-hand side of the right-hand image, you've got these storms forming, rather like the sort of white equivalents of the great red spot on Jupiter. And now we reach the outer part of the planetary solar system. No, I'm not going to be talking about Pluto. We can talk about that if you want. But this is Neptune. And again, Neptune, a blue planet, and it does actually have rings, and it's blue for the same reason as Uranus was. And there we go, I can go back to Uranus. The most important feature I wanted to tell you about Uranus is that it is clearly on its side. The moons around Uranus are in the same plane as the ring that you can see here. It's a very faint ring. You can't see it through a telescope as an amateur. But the thing is, one of the big debates in the astronomy world is why is Neptune knocked over on its side? Why is its axis of rotation almost lying in the plane of its orbit around the sun? There are all kinds of hypotheses. I would say there's probably a paper on this every 6 months, and they're getting better and better at developing them. They tend to be rather complicated. I won't get into the details. But I will go to this last slide here.
Oh, Simon, we have more time. We have JS coming up at 2:30, and then okay. JS takes Attila takes over from JS at 2:30. So we have 15 minutes, and I've got a couple of questions here. So okay. let me know when you can answer them.
Fine. What I'm going to do here, I just want to deal with that question about what stars we can. This is an image of our galaxy. It's obviously an artist's impression because no one's been out that far and photographed it. It's a spiral galaxy. And you can see our sun sitting in sort of an average position. And the important thing about this is that there's a little ellipse that's been drawn around this sun. The ellipse is a little bit out of date now. That ellipse has a radius of about 6,000 light years. The distance between us and the nearest star is about 4 light years, just to give you an idea of distances here. Today, that ellipse would probably be between 8 and maybe 10,000 light years in radius. And the point is that the significance of that ellipse is that that's the ellipse within which the professionals are looking for planets going around other stars. But it's also the ellipse where many of the stars that we can see through our amateur telescopes are actually coming from. So whenever you can see a star and it's resolved as a star, it's certainly a star within our galaxy. We cannot, except for supernovae, we cannot actually see stars, individual stars, certainly not through amateur equipment, in other galaxies. Let's move to questions. Oh, but my point would be, look at how much of the rest of the galaxy we have yet to have a really good look at. Questions?
So Simon, the first question would be from Daniel. At any time, any given time, how many moons would be visible in Saturn's skies?
For most of us, we probably only get to see the one moon, and that will be Titan. Titan is the size of our moon. It's about the same size as the Galilean moons, the 4 key moons that revolve around Jupiter. But I know that people have, with the appropriate telescope and perhaps with an appropriate camera, seen 2, 3, 4 more moons. But the commonest moon, when you can see it, is going to be Titan.
Next question is from Benjamin. How many stars out there, close enough or big enough, can we resolve in a small disk using a powerful telescope?
In a small disk? I'm wondering what he means by a small disk. Let's just assume that he's wondering how many stars we can see. I don't know I can put a number on it, but the point of this, this image here, it gives you an idea that with respect to all the stars of our galaxy, what we can see is in our local neighborhood. There's several reasons for this. One is we can't see through the middle of the galaxy and out to the other side. Principally because between us and the center of the galaxy, there's a lot of opaque dust. But if you look at the image here, you can see that there are arms, bright arms like this one here, but there are also darker areas like there and there. And in fact, here, there are black areas. And those black areas, those are again opaque dust. So there's opaque dust in the core of our galaxy, but there's also a lot of opaque dust lining the arms of the spiral structure of our galaxy. And we can't see through those with either white light or hydrogen alpha light. The professionals see through them using radio waves. So that's why they can actually map out what's on the other side of the galaxy. But in terms of what we can see as amateurs, we're looking in our local neighborhood. And our local neighborhood probably today is probably something like this. And as you can see, it's bounded by dark dust here and bounded by dark dust there. And then here it curves and curves this way. So I can't put a number on the number of stars, but it's limited. Mind you, you'd have to live a long time before you'd actually observed all of the stars that are available.
Good one. Next question is from Keelan. Why is the far side of the moon's surface different from the visible side? And do we see this phenomenon with any other planets, moons that are tidally locked?
Yes, we do. Number one, in the case of our own moon, it's principally because the crust of the moon, the white stuff, which is called a north, for those that know, is much thicker on the far side of the moon than on our side of the moon. When you look up at the moon, even naked eye, you can see that it's basically made up of white highland areas, and then these patches, large patches of medium to dark gray material. The medium to dark gray material is lava, and it's lava of the same kind of composition as makes up the ocean floors on Earth, or the island of Hawaii. It's the volcanic island of Hawaii. And the circular areas that these lavas sit in are called mare, which is Latin for seas, because 400 or 500 years ago, people thought they were actually seas on another celestial body. They do tend to be flat, that's for sure. But the thing is that the holes, the circles that they actually occupy were impact basins. Impact basins, we don't know when they formed. People have been thinking they formed around about 4 billion years ago, but nowadays, most scientists now think that in fact they probably formed much, much earlier than that, probably very close to the beginning of the history of the solar system. But the thing
and a follow-up question. We'll get some good questions here.
I haven't finished the answer on this one.
A follow-up question from Benjamin. So it says that so Betelgeuse and Orion can be resolved by, I suppose, a really powerful telescope, and most other stars are basically pinpoints. What other stars are like this? So similar to the question he asked before.
Let's come back to me with that one in a minute, because I'm explaining the difference between the two sides of the moon here.
Okay.
And the thing is that the lavas that actually form those impact basins, they are actually relatively young. They're somewhere between about 3.9 billion years old and about 3 to 2.5 billion years old. So they actually came up from inside the moon a long time after the impacts that formed the basins they now fill. And the fact that the crust is so much thicker on the far side and so much thinner on the near side means those lavas had a much harder job getting to the surface on the far side and a much easier job getting to the surface on the near side. That's why the two sides look different.
Great.
So we were back to Betelgeuse. What was the question?
Back to Betelgeuse. Betelgeuse, yeah.
Okay, Betelgeuse, if you or I were looking through any of our telescopes trying to look at Betelgeuse, we would see it as a point of light. It might be a bright point of light, but it's a point of light. It's true that the professionals, especially using Hubble, they can actually see that it's actually quite a bumpy looking star, and they can resolve it. Stars further away, they can't resolve. They will still be pinpoints even to Hubble. But the other thing is that Betelgeuse is gigantic. It's called a red giant. And what it is it's a star that originally was quite a bit bigger, probably 10 times at least bigger than the sun. And as it's approaching old age, it ran out of one fuel and started using another fuel. The way that stars operate, they start burning hydrogen and converting it into helium. When they've more or less run out of hydrogen, they cool and they shrink. And as they shrink, the pressure goes up in their interior, and helium is now able to start a nuclear reaction. And helium starts to try and convert itself into oxygen, nitrogen, carbon. And as you go through these various fuels, the temperature of the core goes up. Helium burns even hotter than hydrogen does, but it burns for less time because there's less of it. And so what happens is that the star starts to expand again. And when you've got a hot enough fuel, the star expands such that the outer layers are so far away from the core that they actually start to cool and they turn red. And that's why Betelgeuse is a red star. You can see it red even naked eye. And as it's expanded, it's actually expanded asymmetrically. So it's actually got bumps on its surface. But there are a number of stars like this. I believe Altair in the constellation of Aquila, I believe also is a star with a different shape. Some stars are big enough and close enough that Hubble has managed to show that they're not actually spherical at all, that they're actually rather flattened, a little bit like sort of fat pancakes. But just as this applies really to large stars at specific phases of their life. For us, whether we're professional or amateur astronomers, those stars have to be really close for us to be able to see that kind of resolution.
Thanks, Simon. I think we've got time for one more question before we turn it over to Jean-Sebastian. Earth, Moon, Mars are in the habitable zone. Then why are there, is there no atmosphere either on the Moon or Mars?
Okay, let's be clear on what a habitable zone means. It is a totally meaningless expression. What it means is that for a star of a given size, and therefore a given thermal environment, if you go out to a certain distance from that star, water, which of course is essential for life, can exist in all three of its forms: water vapor, liquid, and solid. Most importantly, liquid. If you go further out from the star, things get colder, and frankly, yes, there's water, but it's all ice. If you come in much closer, there's water, but it's all water vapor. And so in order for life to be able to use water, it needs to be in liquid form. It turns out that for various chemical reasons, it's only going to be in liquid form if there's also gas and water vapor and ice around at the same time. So it's not so much a habitable zone, it's a zone in which water can exist. Now, the Earth exists with an atmosphere for a number of reasons. It's not just because it's sitting in the habitable zone, it's because it has a magnetic field. And that magnetic field protects the Earth and its atmosphere from the solar wind, which would try and strip it away. Mars has no magnetic field, and its atmosphere was stripped away. It's only got about 1% of the equivalent of Earth's atmosphere, and most of that is carbon dioxide. There's next to no water vapor, except temporarily as it's going through seasonal changes. Venus has no water vapor at all. Mercury certainly has no water vapor at all, and no atmosphere, and nor does the Moon. And it's interesting. Mercury has no magnetic field. The Moon has no magnetic field. Mars has no magnetic field. Venus has barely a magnetic field. The reason it has an atmosphere at all is because carbon dioxide is so heavy. It is so heavy that it manages to hang on to its, the Venus manages to hang on to its atmosphere against the solar wind. But things like hydrogen and oxygen, which we need to make water, are so light, they're so easily stripped away. Without Earth's magnetic field, we would have no atmosphere. Without plate tectonics, we would have no magnetic field because the Earth would be too hot inside to generate a magnetic field. And without the Moon, our planet would be wobbling around like a child's top, and its climate, despite the atmosphere, would be so unstable, it's highly improbable that complex life would have managed to form on it. So habitable zone? No. It's a zone wherein you can actually find liquid water. And then if everything else falls into place, then we may actually have a habitable planet.
Thank you so much, Simon. That was really, we got to all of our questions too that I have here. So we got, well, we can turn it over to Jean-Sebastian right now. Thank you, Simon.